I'm grateful to the organizers for giving me this opportunity. So today I'll be speaking on two variable Artin's conjecture. So we know that for prime P, we can consider the finite field if P. And if we take if P star, which is nothing but excluding the zero element, this forms a group under multiplication. So it's a multiplicative group of order P minus 1. And further, we know that this is actually cyclic group. If P star is cyclic, so we want to find what is the generator for this. So, which is for which A belongs to N, this A mod P will generate the group P star. So it is clear from the thing that A generates a P star, A cannot be plus minus 1 or it cannot be perfect square. And Artin's conjecture, so in 1927, Artin conjectured that these are the only obstruction for A to be primitive root for infinitely many primes. So what he proved, what he conjectured that if A is neither plus minus 1 or perfect square, then A is primitive root for infinitely many primes. So if we consider the set NA as follows, so I'm now fixing an integer A for which I'll consider the primes P such that A generates F star. A mod P generates F star. So Artin's conjecture says that NA is infinite. Not only that, he actually proved, he actually conjectured the asymptotic density of this set. So he conjectured that this has positive density in the set of all primes. So where CA is some positive constant. For later on, some correction factor was added in this asymptotic density due to Heilbronn, but no proof was there then. In 1967, Hull made a breakthrough. So he proved Artin's primitive root conjecture under GRH from some certain Dedekind zeta functions. So this is under GRH. But unconditionally, the proof is still open. The conjecture is still open. So what we consider now that instead of taking the generator, we are taking two multiplicatively independent elements. So I'll just denote by MI throughout the talk, multiplicatively independence. AB multiplicatively independent means that log A and log P are linearly independent. So we are just considering instead of NA, considering the set NAB, the prime P such that AB generates P star. So this is a weaker question than that, and we are asking, can we answer this? So in 1984, Gupta and Ramurthy has a result in this direction. So they have proved the following, that if PQR not P, QR is be 3 primes. So from the monad generated by QRS, they could find a set is subset of the monad generated by QRS with cardinality 13 such that there exists A belongs to S, for which NaX has, okay, so I did not, okay, so since I did not define here, this is just the primes up to X. So NX has lower bound X by log square X. So in particular, if we think that we are getting nothing but, if we consider this notation, the QRS mod P is actually a P star. So instead of getting 2 primes, we are getting a lower bound for A from the set of mode generated by 3 primes. Okay, so in the next year, Heath Brown improved this result. So he has proved the following, that let QRS be 3 multiplicatively independent integers with such that none of QRS minus 3QR minus 3QS is perfect square. Then there exists A from this 3 element set such that A is primitive root for at least X by log square X plus. So we can see that here we are finding A from a 13 element set. So the probability of finding A is 1 by 30, and here it is 1 by 3. We want to see it, the probability should be 1, so that we choose 1 and that will be the primitive root for invariant limit primes. Not only that, we can, if we take that QRS at 3 primes, then we will see that except at most 2 primes, every prime will be primitive root for infinitely many primes. And this follows as a corollary from this, because QRS, if I take primes, they are multiplicatively independent and none of this is perfect square. So at least one of them will be primitive root for X by log square X primes. But we don't know which prime will satisfy when we don't know a single integer which satisfies this Artin's conjecture. So we wanted to ask further weaker questions so that we can approach those. So we'll ask here that A being multiplicatively independent, and we'll define the set PAB as P primes such that B mod P is in the set generated by A mod P. Now if we write NA in this pattern, we'll see that N is nothing but the set of all primes such that A mod P is a P star, which means that B mod P is either in A mod P or it is divisible by P for all B belongs to Z. That's right. We can see that this PAB is much bigger set than NA. We want to understand whether NA is infinite or not. So the obvious question to ask is PAB infinite? So this setup was introduced by Mori and Stephen Hogan in 2000. And they have termed this as 2-variable Artin's conjecture. So this answer turns out that it is Yes, and it follows from a special case of a result of polio. And what Mori and Stephen proved, they proved that under GRH, that PABX, which is the similarly defined, P less or equal to X, P is PAB, this has positive density. So the first unconditional lower bound, we want to understand what is the size of PAB because this is conditional. The first unconditional result was due to Ramurthy, Shekwe and Stewart in 2019. So they have proved that if mod is not 1, then PABX has lower bound x by log square x. So in a recent work with Professor Ramurthy and Josna Shivaraman, we have improved this lower bound. Our result says that so we let QRS be multiplicatively independent and such that none of QR is minus 3QR is perfect square, then there exists a pair AB from the set QRS cross QRS such that PABX has lower bound x log x by log square x. So our method was inspired by the work of Heath Brown, and we can see that in the classical setup, we are getting x by log square x lower bound. But since we are working in the two variable setup, we are gaining by this log x factor. So now we want to just state one ingredient for this proof. Is a Bomberi-Vinaigrette of type theorem, which is by Bomberi, Friedlander, Ivanich, which is modified by with Brown. So it says that let AK some positive integers which co-prime, and for any Q says that K is co-prime with Q is co-prime with K, let UK be the common congruent solution for simultaneous congruent solution for UK congruent to A mod Q and UK congruent to 1 modulo Q. So we have two positive integers co-prime, and for any Q, this UQ is the simultaneous solution for this congruence relation. Now we'll fix one greater than 0 and real number theta, which is less than 4 by 7. Then I'll come to this definition, well factorable function. well factorable function is lambda. I'll come to this definition. So this is the sum over qk equals to 1, and lambda q is that functions value at well factorial functions and q, and this is the difference. What is pi x q? This is p lesser or equal to x, such that p is congruent to uk modulo qq. And Lix is a logarithmic integral. So this has lower bound. UQ is the solution of this simultaneous equation, that x congruent to, since KQ are co-prime, I'll have by Chinese-Diameter theorem. Okay, I'll define the well factorable function. So an arithmetical function lambda is said to be well factorable if well factorable of level Q if there exist Q1, Q2 and lambda 1, lambda 2 to arithmetical function with support one Q1 1 Q2 respectively, with the condition that Q1, Q2 equals to Q and lambda 1, lambda 2, lambda 1, convolution lambda 2 is lambda. Here is one more condition, that lambda 1, lambda 2 are bounded. So I'm taking off lambda well factorable of level Q of order 1 here. So I'm just writing 1. So lambda is well factorable function of level Q if we get two real numbers Q1, two integers, no, two real numbers Q1, Q2, such that Q1, Q2 is Q, and two arithmetic function lambda 1, lambda 2 with support this, such that lambda is convolution of lambda 1 star lambda 2. So here this lambda is well factorable function with level x power theta, where theta is less than 4/7. Now, if we get this result for any theta less than 2/3, then we can refine our result a little bit. So we'll get then that let QR be multiplicatively independent, such that none of QR minus 3QR is perfect square. Then there exists a pair AB from the set QR minus 3QR, such that PABX has lower bound x log x by log square x. So here, instead of taking 3 integers, we are working with 2 integers, and we are getting that log x factor. Thank you.